People usually tended to write down equations and try to solve the equations and things like that. I was not doing that. I was looking at general features that spacetimes can have. I think the point has got lost. It's missing something. They've lost it in the power of computing. The thing is that computers have got so powerful that they've lost the thread of what they're doing. The complex numbers are absolutely fundamental. You see, they're fundamental to quantum mechanics. The whole structure of quantum mechanics depends on complex numbers. Twistor theory is very specific to space-time geometry.
So your Nobel Prize is for what?
It's for showing that was wrong, if you like. The name is wrong. It's not artificial intelligence. It's not intelligence. Intelligence would involve consciousness, that these devices are not conscious, and they will not be conscious unless they bring in some other ideas.
Host of the interview is Dr. Matt Kawecki, a science popularizer and a former digital ambassador of the European Union.
If you remember from your childhood the moment that you touched the geometry for the first time.
You see, I tell this story as a joke. Now, a joke doesn't mean I really mean it as a realization. The joke is as follows. When I was very young, I was probably about 6 or 7, I hated spinach. I was given this spinach to eat, and I said, "No, I don't like spinach, and I'm not eating it." And the person who was dealing with it said after a while, "Look, okay." You didn't use the word okay in those days. It would mean all right. All right, if you eat half of it, that's enough. So when she wasn't looking, I took this circular patch, reconstructed it into a semicircle of the same volume, but now shaped in a semicircle. And she came back and said, "That's good. Thank you very much. They can go." I guess it was that the volume is different from shape. I think it was a rather elementary discovery.
Is it true that when you found out about your Nobel Prize, you organized a meeting on Zoom? Supposedly you said that you didn't deserve the Nobel Prize, that you show the singularity exists, but not that they are hidden behind the horizon of events.
Yes, well, this is well known. It's all part of the story. See, some people get confused by the story. And the Nobel, what they say it isn't completely correct, what they say. You see, it's the right idea. But how do they say it anyway? It's difficult to say. And it depends what you mean by the words. You see, what I showed was what... See, when I collaborated later with Stephen Hawking, he used a certain terminology which was different from my original terminology. However, it is the terminology which I'm now going to use. What I'm now going to use, which is not actually quite my terminology, it's Stephen Hawking's terminology. Okay. What I did prove then was that you got a singularity. Now this was if you have a certain criterion for a collapse, which is beyond retrieving, a collapse gone past the point of no return, which I phrased in terms of what I called a trapped surface. That was really the key point. That if you have what I call a trapped surface, which would happen in a collapse. You see, there was a famous paper by Oppenheimer and Snyder. This was in something like 1939, just before the Second World War. And in this paper, they had a dust cloud which collapsed, and it became singularity, infinite density. So the collapse became infinitely dense in the middle. Nobody really believed this because, unusual, it wouldn't be so spherical and you'd have pressure. In the Oppenheimer-Snyder picture, there was no pressure. It was just what they call dust, no pressure. But more importantly, exactly spherically symmetrical. So exactly everything falls towards one point. That's not realistic. And this was a time when these quasars were being seen and there's something really funny going on in these distant galaxies. Huge activity. It looks as though there were bodies out there which were beyond the limit that you would get in the Oppenheimer-Snyder model. In fact, beyond my... Well, you see, I didn't have my theorem at that time. My theorem was developed as a response to the arguments that people had. They say, well, the Oppenheimer-Snyder picture is not realistic because it could be very irregular and it could swirl around and come out again. And this was the common belief because in addition to the observations, there was a paper written by two Russians, Lifshitz and Khalatnikov, and Lifshitz and Khalatnikov seem to have proved that in general, if it's complicated, you will not get singularities, that the things will not become infinite density, they will swish round and come out again. So this was the view that people had formed largely on the basis, I suspect, of this paper by Lifshitz and Khalatnikov.
So your Nobel Prize is for what?
It's for showing that was wrong, if you like. No, yes. You see, my Nobel Prize was to show, I had a look at the paper. I didn't really believe their methods. I thought that's not convincing enough. There was a mistake in the paper, which Belinsky became a collaborator with them later and corrected the mistake. And then they found that singularities were generic.
Do you remember that moment that you found that mistake?
No, I didn't find the mistake. It was Belinsky who found the mistake. No, I found an independent show that there must have been a mistake. Mm-hmm. But my argument was nothing to do with the paper. It was using completely different methods. And I was looking at methods which I guess people had never used before. That's probably why that's what the prize was really about.
When you look at your life, you are more mathematician or physicist?
Mathematical physicist. So I was using mathematical techniques.
But what's closer your heart?
That's a difficult question. I think it's drifted more to physics than it probably was more mathematics earlier. You see, when I go to the Cambridge meeting on Twistor theory, and I learn all about what many people are doing, a lot of it is very mathematical. It's interesting, but it's not where my heart is, if you like. Where my heart is the physics part. That part of Twistor theory which is connected with physics. Twistor theory has grown outside that area. It's grown into a much bigger mathematical area, which is interesting to me, but not so near my heart, if you like. It's not what I like to develop, not what I work on. So what I work on is where the mathematics ties in with the physics. It's hard to separate them in this sense. So it's mathematical physics. Yes, the Oppenheimer-Snyder model, that's right. So I started thinking about this independently of that. I wondered, well, suppose it is very complicated, and I imagined being inside what you call a black hole. Getting near these singularities and what it would be like, and I tried to imagine that. And I'm not quite sure, you see, the techniques which I had developed came from a different area. I was looking at a different problem altogether. And I developed some of these techniques of looking at the causal structure. You see, people usually tended to write down equations and try to solve the equations and things like that. I was not doing that. I was looking at general features that space-times can have. And if you have a region in space-time, and you look at the future of that region, so look at all the places that can be reached in the future. This point may not be reached, this point can be reached. So into the future, it sweeps out a region. Now what does that region look like? What does its boundary look like? What does the edge of it look like? It looks like something which has light rays on it. So I could prove that. You could prove a theorem which says any point on the boundary must lie on a light ray. Anal geodesic. This way into the future, but not into the past. If you go into the past, it may wind round and round and never end. It may wind round and round, or it may go back to the initial point of this thing you start with. So it's quite complicated. But I understood quite a lot about that kind of structure. And I was able to show that once you have what I call a trapped surface, which is a general thing. You see, it doesn't... See, in the Oppenheimer sniper picture, he had to assume exact situation. I'm not assuming any exact situation. I'm assuming an inequality. So it has to... A certain thing has to... How do I put it? It's difficult to explain, you see. There's a thing called a trapped surface, which I introduced. This was a notion which people hadn't thought of before, that can you surround your body by a surface, so it's an ordinary two-dimensional surface, such that the future of that surface, you look at all the things which can be reached into the future from that surface. What is the edge of its surface? What does it look like just at the initial state? And the claim is that if the light rays at the beginning are converging, that was my condition. A trapped surface is if the light rays are converging, both the in ones and the out ones. You see, how do I put this? A surface element in space-time it's a space-like thing, so it could be an instantaneous surface. It could exist just for a moment. Now, suppose it's concave, like that. Then the rays, if you imagine a flash of light on that surface, the rays on the inside will converge, and they will come closer and closer, and they will start meeting each other. The rays on the outside will diverge, they'll never meet each other. If it's the other way around, then they will converge in this way, and the other ones won't meet. There are certain surfaces in space-time which converge on both sides. You think it's a rather peculiar situation. It's not so peculiar as you might think. I won't go into the discussion. You have to bring in the time as well as the space.
When I look at all your concepts, very often you talk about your work with Stephen Hawking. I think that's my private opinion, of course, that almost all these concepts were more Penrose than Hawking. That Hawking was much more better getting attention.
Well, you see, on this topic, I would say it was mainly me, that's true. Well, I would give some credit also to Brandon Carter. You see, Stephen Hawking worked... In his early work, there were lots of mistakes. And usually it was Brandon Carter who corrected the mistakes. But he corrected them himself. The mistakes, he was good enough to see when they were mistakes, and he corrected them. So the final results he had in his thesis, I was one of the examiners of his thesis, and I had listed the various mistakes in this thing, but he'd corrected them all by the time the exam. So that was okay. But these techniques were, he did develop some of them beyond what I'd done. But the main ideas came from me. I think that's true. Of course, the most important work that he did was really quite different. It was the work on black hole. I mean, he did a lot of hard work on it, so I wouldn't discredit what he did. He did a lot of hard work. It's not just me. No. I would say the initial ideas came from me, but a lot of the technicalities which came later, he worked out himself. And that's true.
There's a lot of figures, Penrose cube, Penrose stars, never-ending numbers of creation. It's more science or more your game with the reality, your game with the humanity?
I don't draw a clear line between games and serious science. How do you know when it's serious science? I mean, the non-periodic, if you look out at my tiling out there, and in the back of...
Because, it looks like a game with our minds.
Yeah. But then a lot of mathematical physics is games, in a sense. You see, you do it for fun. It's a combination. You see, partly you have a drive to find an answer to a problem, but often it's you do what looks fun. And I quite like playing with these causal spaces. So you're looking at at how space-time structure in general terms, or what the boundaries of futures look like. And that was the kind of thing that was used for the theorem, which eventually got the Nobel Prize. You see, that was a kind of mathematics which I had developed, not particularly originally to prove this theorem. The techniques were just being developed for fun, if you like, to see what things looked like in space-time, what the boundaries of futures look like. And it's an interesting subject. And in mathematics, that's what one does. One often is interested in a subject just because it's entertaining to one. So you do it because you like it.
A lot of scientists, people worldwide, call you the greatest mind in the world, genius.
Well, that's
I don't ask you...
A limited number of people, I hope.
I don't ask you if you agree or not, but I would like to ask you, what are you doing that having 93 years, you are in such good condition? How you are spending your day now?
Well, I'm rather slow. I think I'm getting very slow at things. I always used to be rather slow, but I've got slower. Also, I find that, people say when you get older, you start to lose your recent memories. I find I lose my distant memories. I can't remember what I did. And somebody say, oh, you did that. Oh, what? Oh.
1 hour ago, but you are still remember any details of the theories,
These
conspects.
old things. No, the old things I lose, you see. I'm losing my long-term memory. No, I don't know if it's really losing.
But what's your advice for the people?
I'll tell you my advice. My advice is to be lucky. I think of so many things in my life which depended on pure luck. It's very hard to tell, you see. I think I had to be in the right place at the right time often. That's certainly true. But I also, let me consider, say, work that was developed. See, my early interest in general relativity, serious interest in the sense of working efficiently on the subject rather than dabbling, was, well, Hermann Bondi was doing things on gravitational waves and how the mass gets carried away by gravitational waves. And the most important work was done by Ray Sachs. Mm-hmm. Ray Sachs, he died quite recently. And he had a very important result, a very beautiful result, which had to do with the way that the radiation field behaved. And he developed this idea of what he called the peeling off theorem. There are these certain directions which you get in the curvature tensor, and the most distant, they all point outwards, and then you come in a little bit, and then one doesn't point, and then they a bit more, and he said they sort of peel off as you come in. Very strange way of behaving. But then I remember some moment when I was thinking about this, and I realized that this had to do with this conformal. It was the birth of conformal infinity, really. The way of talking about asymptotics was to look at the conformal picture. You see, when you look at it conformally, all these things come together, and you can see why the peeling theorem happens. But that was very much the fact that I knew Ray Sachs, and I'd learnt about his result, and I got the key point out of what I was doing came from what he did. Engelbert Schucking, I happened to share an office with him. Pure coincidence. I shared an office with him, and he explained the importance of the conformal invariance of Maxwell's equations. I had no idea about that before, and the importance of the splitting of positive and negative frequencies. But that led me to Twistor theory. If I hadn't shared that office with Engelbert Schucking, would I have had those ideas? Probably not. I have no idea. So luck, yes, luck is important.
Nobel Committee and AI takeover.
Do you agree with that year Nobel Prize committee when you look at the Nobel in physics for fathers of AI?
I haven't looked at the details of it. I don't know what they say.
For fundamental work under synthetic neutral networks for Geoffrey Hinton. Is it physics?
I'd be rather doubtful whether it's really physics. I'm not sure. You see, the Nobel Prize has, you might question some of their decisions sometimes. I would question a few of them. Maybe I would question this one. I'm not sure. You see, I haven't looked at it carefully. It depends exactly what they say. You see, it's a technological advance, I would say. It's probably making use of... I mean, is it a theoretical advance, or is it... I don't think so, is it? But I mean, the Nobel Committee normally doesn't give the prize for purely theoretical. I mean, it doesn't.
It doesn't, yeah.
You have to have a physical application of it. Yes. Now here, I'm not quite sure. I'd have to see what the wording is in the Nobel Prize to say whether I'm happy with it or not. I don't know.
How do you look at the AI development, and what's your prediction about the future of AI?
See, I don't really know what AI does these days, you see. So you're asking me a question outside my area of expertise. I would say an area of expertise has to do with whether these devices actually do what we do. I don't think they do, because they're not conscious. I don't think they will ever become conscious by virtue of being computers in our current sense of the word. I don't know if that's an answer to your question. It doesn't mean that they won't be better than us.
The biggest risk of AI development is?
Yes. So I have nothing against that. That's fine. I think there is a risk involved here. Part of the risk is people thinking that they're actually...
That there is a conscious.
They're conscious, yes. There might be an even more of a risk if they were conscious. You see, maybe one could understand what's involved in consciousness and develop some kind of device. I'm not calling it a computer, because in my view, it would not be a computer. It would be something else, some device which is conscious. And since I believe consciousness is a physical process, I don't think we understand it. I think it involves the collapse of the wave function. That's partly a negative conclusion from, I don't see it anywhere else. But the collapse of the wave function is very mysterious and involves certain retrocausal things, which are a little bit puzzling. I think the way that time works is not so clear when you're talking about, but there are certain things which are in contradiction, you almost say, with ordinary causality. It's not so much that they are, it's that you have to have different concepts of what you mean by reality. And there are two concepts which I've tried to separate from each other. One is classical reality, and the other is quantum reality. Now, classical reality is the sort of thing we normally talk about.
We can touch, we understand, using our senses.
Yes,
yeah.
but the main difference I'm saying is you can ask the system, say, if I take this glass, and I can ask the glass, I can say, hello, glass, what shape are you? And don't do it that way, but I say, okay, what shape is the glass? And I say, oh, it's got a round top, it's more or less cylindrical.
And that's the classical world.
It's classical reality.
Yeah.
Now, quantum reality is more like, well, Einstein had a nice criterion, but he didn't call it quantum reality. I'm calling it quantum reality. This was, how do you know that the wave function is real? Is the wave function of a particle real or not? And a good example of this is the spin of a spin-half particle. Now, the spin of a spin-half particle is a quantum thing. Now, can you ask the system, hello system, which way are you spinning? It does not. It looks at you blankly and says, I don't answer questions like that. Ask me a different kind of question, please. The right thing to do is you say, okay, particle, is your spin in that particular direction? You see, the spin has an axis. Mm-hmm. The way that spin works, for a spin-half particle, it has a particular axis. That's how you describe the quantum state of a spin-half particle. It has one particular direction, and it spins about that direction. Now, can you ascertain that direction? No, you can't. It's quantum reality. You cannot ascertain quantum reality. You can only confirm it. So I like to use those two words, ascertain. I can ascertain the shape of this glass. That's classical reality. I can only confirm quantum reality. I can, if I think I know which direction it's spinning. I said, yeah, I've got my calculation done. I said, you've done this, blah, blah, blah. Yes, it's probably by now spinning that way. I say, hello, state. I think you're spinning that way. Have I got it right? And if I have got it right, it says yes with certainty. So that was Einstein's criterion. So if you can confirm with certainty that then it gives you an element of reality. He called it an element of reality. I'm calling it an element of quantum reality. Classical reality is the other kind. You can ascertain classical reality. You can only confirm quantum reality. And you need those two ideas, and you need to separate them. And quantum reality behaves very peculiarly. It actually behaves retrocausally, what you might think. There are these experiments with, I think you talk about the Nobel Prize, the one before that one, to Zeilinger and people about these, I think, EPR-type experiments. I can't quite remember what they got it for, but it's something like that. You have these effects which seem to affect the instantaneous. You see, you share a spin between Alice and Bob, and Alice and Bob originally have a spin 0, and their spins are opposite. So if Alice's spin is this way, Bob's is this way. Now suppose Alice measures her spin and she finds it to be that way. Retrocausally, along the past light cone, so it's not just simultaneous, worse than that. It's into the past, but not faster than the light could go from this one to this one. It's a strange way around. But retrocausally, it becomes the opposite of Alice's measurement. Bob can't ascertain it, so she can't send a signal faster than light because he can only confirm it. He doesn't know which way it is. So you need that idea to make sense of these EPR, Einstein-Podolsky-Rosen type experiments, which I think, I'd have to check exactly what the Nobel Prize was the year before this one. But I think it was to do with that. That's a very important and fascinating discovery. But to understand what's going on, I think the best way to do it is using quantum reality. And you certainly can't send a signal faster than light by these means, but you can retrocausal backwards faster than light, or not as fast, almost as fast as light, backwards, if it's only quantum reality.
As long as we don't understand how quantum world work, we cannot replace it into
I
the
think it's not
digital
as bad as that. You see, don't understand is saying, rather trying to put it into a classical perspective. We can understand the mathematics of it, and we can get used to it, okay? And that is involving an understanding. If somebody asks me a question, I may not understand it that well, but I could do my best, and I might understand the quantum mechanics well enough to give the answer that quantum mechanics would say. Now that means understanding. Sure, it's an understanding of what's going on. You know, there's this famous comment, was it? Nobody understands quantum mechanics, was that?
I know
maybe it was Bohr or somebody.
Bohr. I think
it was Bohr, yes.
Yeah.
No, you see, I think that's misleading. You see, understanding doesn't require it to be a classical understanding.
We are determined by the nature to understand the classical world. Quantum world is indeterministic and it's ununderstandable for our mind a little bit. You need to use the formulas to try to understand the quantum world.
I think it's unfortunate to use the word understanding and limit it. You can say, I don't know what word to use, but if understanding in the sort of classical sense, and that fails. Yes, that does fail. But it's not lack of understanding. You get the picture, and you can see, oh yes, I know how to make the predictions in quantum mechanics work, and they can be quite yes-no predictions. Some of the predictions don't have to be just probabilities. So I think the view is it gets sort of mixed up with the idea, oh, you only know the probabilities or something. I think that's misleading. These things are puzzling not just because they're probabilistic. They are sometimes just probabilistic, but that's what makes them consistent by having them only probabilistic. But the things which I find most fascinating about quantum mechanics are not probabilistic things. They're like these EPR effects. Sure, it's probabilistic if you ask somebody to make a measurement and it's only a quantum reality that he's trying to make a classical reality measurement. He's only going to get a probability answer. I just think one has to separate the quantum reality from the classical reality and realize that the quantum reality behaves differently. Yeah.
Fully.
But it doesn't mean it's beyond understanding. I don't know if that's the way people use the word understanding often in that way. I think that's a bit misleading.
AI takeover.
A few times you talk about the Nobel Prize. We're back from Stockholm. This year we've been there interviewing Nobel Prize winner. Don't you think that this year Nobel Prize is the tribute to the Nobel Committee for Artificial Intelligence? Nobel Prize in Physics, fathers of AI. Nobel Prize in Chemistry, Sir Demis Hassabis, co-founder of DeepMind, that's AI system. David Baker, computer vision, digitalization of proteins. Don't you think there's a tribute for AI?
I see. Well, you have to be careful. First of all, the name is wrong. It's not artificial intelligence. It's not intelligence. Intelligence would involve consciousness. And I've always been a strong promoter of the idea that these devices are not conscious. And they will not be conscious unless they bring in some other ideas. They're all computable notions.
But intelligence, it's not consciousness.
It depends on consciousness. You see, well, it depends on how you use the word. I think when people use the word intelligence, they mean something which is conscious. I mean that. You see, I developed my own ideas after going to a course. You see, when I was a graduate student in Cambridge, I went to 3 courses which were nothing to do what I was supposed to be doing. One was by Bondi on general relativity. One was by Dirac on quantum mechanics, very distinguished Paul Dirac. And the third subject was on mathematical logic. And I learned about Turing machines and the notion of computability. And I knew what computability meant. And I learned about Gödel's theorem. And Gödel's theorem I found stunning because it told you that there are things that the understanding transcends the use. Let me put that more clearly. What Gödel does, it's very clever. What he does is to produce a statement. Now, suppose you're trying to develop your mathematical methods of proof. What do you mean by proving a theorem in mathematics? How do you know it's really true? Well, you prove it. What does proof mean? Well, you see, does it mean, okay, you've got a set of rules, and if you follow these rules, that makes it a proof. Mm-hmm. Now, how do you know these rules only give you truths? Well, you've looked at them carefully and you say,
but maybe AI creates its own rules.
No, you see. You have to be careful about this. This is the point. But I learned from Steen. This was a man called Steen, who was a logician. And I learned from him this important thing about Gödel's theorem. Now, Gödel's theorem is extremely clever. You make a statement which asserts that it cannot be proved by these rules. It's just, the clever thing is to make it do it. It says, you give your rules, which you regard as the rules of proof, and you could put them on a computer. So that means they're computational rules. Now, I knew that there were things that you cannot put on a computer. I learned from this course that there are non-computable things. There are things in mathematics which are not computable. Now, what does computable mean? It means that you can make a computer. Well, you have to define what a computer is. And Turing had one definition of a computer. There were several other, Church and Curry, Other people had their definitions of computing. They all turned out to be equivalent. So there is one universal notion of computability, which is what you mean by what can be done by a computer.
But maybe this is only language problem, that the language development has not kept out the development of AI. Maybe we have just only a language problem, that we cannot, describe what we created.
No, I don't agree with that. It's not a language problem. You see, you make your new language. Sure, you can do that. You make your new language. And that's what you can do. See, let me describe the Gödel theorem, how it works, you see. See, the Gödel theorem says you construct a statement which says, you see what it means. The way you've constructed the sentence, you can see what it means. And what it means is, I am not provable by those rules. And it does that. It really says that. Then you see, okay, well, perhaps it is provable by the rules. If it is provable by the rules, then it must be true. Well, I've said it the wrong way around. Doesn't matter. The other way, suppose it's false. Then that means it's provable by the rules. And if it's provable by the rules, you've understood the rules, you said, you looked at them all and said, yes, that's okay, that. Sure, if you follow those rules, it is true. So that means you believe that the rules only give you truths. So therefore it is true that it's not provable by the rules. If it's false, you see, then it is provable by the rules, and therefore it's true. So it has to be true and not provable by the rules. I found that amazing. You see, that's the whole point about the Gödel theorem. The whole point, as far as I'm concerned, about the Gödel theorem is, how do you transcend the rules? And that's what you do, by understanding them. You understand them, why they're true. It's not that you use the rules, but you understand why use of the rules only gives you truths. And that's how you can prove things which go beyond the rules, by knowing why they're true. Now, knowing why they're true, well, what does it mean? Well, it means you understand them. What does understand mean? You've got to be conscious of them. You see, the wording is clear. It means that you have to know what you're doing. You have to know why they're true, not that they're true. You can be told that they're true. You can learn at school that they're true. That's not the point. You have to know why they're true. Why they're true needs understanding them. And understanding them requires being conscious of them. Now you see, the point I was making is that consciousness enables you to transcend the rules. You see why they're true, and that goes you beyond it. You see, what the Gödel theorem does, it tells you how to use your understanding of why the rules are true to transcend the rules.
You think that AI is the simple tool or simple thing that we can use in the single case?
No, I don't say it's single. It's obviously infinite. No, clearly, that's not the point. The point is it doesn't know what it's doing. That's still true with AI. You talk to an AI thing, it doesn't know what it's doing. It speaks from experiences, if you like. You see, people have confused the story. The story is they've lost it in the power of computing. The thing is that computers have got so powerful that they've lost the thread of what they're doing. I think the point has got lost. I think Turing wasn't too far off. You see, he was a little bit confused person in a way, because it was not clear what he believed. But he did call this thing the Turing test. How do you decide whether an entity is conscious or not? Well, you have a conversation with it. You talk to it. It's missing something. I think, that's the trouble. You see, obviously it has a role to play. I'm not going to say that. Clearly it has a role to play. It has a role, but you mustn't be confused. The fact that it has a role to play, it's to do with the power of computation. Sure, computers have got so powerful now that they can do things way beyond what humans do in computing, sure. And you can take a mass of data, and you can analyze that data, and you can see what the data says, and does this thing in accordance with previous things in the data, or is it not? And AI, that's all it does. It doesn't understand what it's doing. And understanding is different from computing. No, I think people have lost the plot, yes. No, that's true. You see, I wrote my book, The Emperor's New Mind.
But what does it mean that people lost the plot?
Yeah, I think they've lost the plot. Because the whole point of my train of thought was, we've got to find something in physics. You see, I believe, I'm a physicalist, in that I believe whatever is going on in our heads, whatever creates consciousness, is part of the physical world. I don't believe it's magic that comes in from who knows what. What I claim is saying that the physics that is involved in conscious thinking has to be non-computable physics. Now, the physics we know, there's a little bit of a glitch here because it's not completely clear. But as far as we can see, the physics we know is computable. You see, what about general relativity, where we have wonderful machines which compute what black holes do when they spiral around each other and produce gravitational wave signals? And you can say, yeah, that is a black hole collision because this has this very clear feature, and yeah, you can do all that. That is fine, but that's not what I'm talking about. What I'm talking about is the physics has to be a physics which is, in principle, non-computable. So AI can go ahead as much as it likes. It's not going to be able to get this. You talk about a black box, but you don't know what's in that box. Is it a computer? Is it a computer of the kind we understand now? Is it something which involves a physics which involves a non-computable process? Not so far. I'm not saying that won't happen. I dread it because I don't want it to happen. I can't help it because I suspect it will happen someday. But it's not AI as we now know it. AI, as we now know it, is computer-driven. And that means it's not going
Superhumans, AI will never exist?
Well, the trouble is that AI is a bad term. It means artificial intelligence. Now, intelligence, in my view, is conscious. That's what intelligence is about.
Okay, so how I can call it?
Artificial cleverness. How about that? AC. You can see the difference to some extent when you do mathematical. You have mathematics students. Some of them understand what they're doing. Some are just clever. They can repeat what they've learned. They know how to do it very cleverly. They can calculate very well, but they don't necessarily understand what they're doing. The physics we don't know involves non-computability. So that's my claim. So I made this claim in The Emperor's New Mind, and I've made it a little bit more forcefully in Shadows of the Mind.
I mean that maybe it's not the consciousness. Maybe it's something absolutely new. Maybe that's not awareness.
But there may be completely unknowns which we have no concept of at the moment. That could be true. I'm talking about things. You see, if you're talking about AI, that means, unfortunately, it's a bad term because it says artificial intelligence. Whereas to me, when people use that term, they mean things that can be done by computers. That's what they mean. They have computers, and their computers are very powerful. And then what they mean by AI is using computers. It may not be using in a straight logical way. Usually, I haven't studied these things, so I'm probably out of date. But as far as I can see, what it is you look at masses of data, and then you sort of look for patterns, or you try to analyze it in that kind of way. But it's all computational. You're using computers. By its very nature, it's computational. The word means computational, means by a computer. Now, a computer is a very specific kind of mathematical structure. It means computational mathematics. If you study the mathematics as an abstract subject, you rapidly learn that there are things way, way beyond computability. It's a very limited part of mathematics. Some of the mathematics that's involved is not computable. You can't get at it by an algorithm. Now, you see, people often think, well, AI doesn't use algorithms because it's using these sort of random methods or something. I don't know. I haven't studied in detail what AI really, what is called AI, really involves when you put it on a computer. But it is being done by a computer, so it's still something computational, no question about that. I'm claiming that you want something non-computational. Now, you see, people tend not to believe this because they just think of computers and they don't know there are non-computable things. If you study the mathematics, the mathematical logic, you see that there are non-computable structures. The logic, the physics of the world could easily be non-computable. And my view is that, yes, it is non-computable. And that somehow nature has been clever enough to produce beings which can tap into the non-computable aspect of the physics. And they managed to do this using natural selection. I have no idea how far down the animal kingdom goes. Humans are certainly conscious. I believe anybody who owns a dog is absolutely convinced that dogs are conscious. I believe it. Cats, probably. Elephants, certainly. Way down, way down, probably. Octopuses, I'm sure. I don't know. Is a bacterium conscious? I have no idea. Is a frog conscious? Probably, yes. Is an amoeba conscious? I have no idea. I'm just speculating. I've no real reason for believing these things. But I think consciousness is something different. It's not computational. And the thing is that it's just people are so hypnotized, I shouldn't use a rude word like that really, by the fact that computers have got so powerful that, yeah, there's the answer. The computers are so powerful, we found the answer. It's just computers. I'm saying, no, it's not. The answer is something much more deeper than that. It's not more complicated than that, it's deeper than that. It involves a kind of physics which we don't probably know yet.
It's deeper because it's based on the quantum world?
It's beyond the quantum world. You see, the quantum world is still computable. What's not computable, as far as we know, there's a basic unknown in quantum world. The quantum theory is fundamentally incomplete. I call it even wrong in a certain sense, because it believes that quantum superpositions persist at all levels.
The Twistor theory.
What is a Twistor theory?
Which describes the structure of space-time in an unusual way. So rather than thinking of space-time, which is a four-dimensional space, three of space and one of time, and a point represents a moment which has a momentary existence. So it's the basic element of space-time is a point, and then you built it out of the points. Now, in Twistor theory, you take a different point of view. The basic element is not so much a point, but as a light ray. So you think of the history of a photon, if you like, which is a line in space-time. It's what's called a null line. It's travels at the speed of light. Well, light ray would. And if you like, your analog of a point is a light ray. It's actually not quite that. It's more than that, because the light ray is only the trajectory of a photon. The Twistor idea incorporates other things like the momentum and the angular momentum of the photon. However, and the spin of the photon. You see, photons have a helicity and a spin. The helicity depends on which way it's spinning, right-handed or left-handed. And when you incorporate the handedness of the photon, you find it's not completely localized. And there is a structure which is not localized along a light ray, but spread out in a certain way. And it twists around itself. And this twisting configuration is the origin of the name, Twistor. So that the element has this twisting characteristic. But the original idea of the subject it has a sort of complicated history. Let me try and explain it. It came from basically two ideas. You see, when I was, I think it was in 1961, 62, I think 62, I think. I was in Syracuse University. I had done my PhD in Cambridge, and I then went and did some research, mainly at Princeton. And then I was at Princeton on a fellowship for a year and a half, and it was a 2-year fellowship, and the other half of the year I spent at Syracuse in New York State. And I shared an office with Engelbert Schucking, who was a German who'd left Germany just before the war, and he was a very original man who knew everything, and also he knew everything and everybody, and original, which is unusual. But I had discussions with him, and he explained that two most important things, one most important thing of quantum field theory, which had to do with the splitting of fields amplitudes into positive and negative frequencies. It's hard to explain what that means, but it depends on, normally where you do it, you do a complicated kind of thing called Fourier decomposition. You spread things into different frequencies, and then you take the positive frequency and not the negative frequency. That's a complicated thing to explain to somebody who's not a scientist. But then the other thing he told me about was the conformal invariance of the Maxwell equations. The Maxwell equations describe electricity, magnetism, and light. An amazing set of equations, and they theoretically explain light, which is an amazing thing. Light was a quite complete mystery before this. And the different frequencies that you have and the ones that we don't see, and all that sort of part of Maxwell's equations. But it described electricity, and it was a sort of unification of these ideas, electricity, magnetism, and light. And the Maxwell equations, another thing Engelbert Schucking mentioned to me, was that the Maxwell equations are conformally invariant. Now, what does conformally invariant mean? That means that it's independent of scale. So big and small are equivalent. People might be familiar with the pictures of the Dutch artist M.C. Escher. And there are pictures which depict a sort of universe with angels and devils in them, and it's all within a circle. Mm-hmm. And then the angels and devils, you get towards the edge, they look smaller and smaller and smaller, but they're conformal. That the shapes, especially small shapes, if you look at the eyes of the devils, you see they're exactly the same shape, even though they get smaller as you go to the edge. So this is what's called conformal. And conformal way of looking at physics was very important to me, because it led to various things. For example, how you talk about radiation and fields and infinity, and you use the Escher trick by bringing infinity to a finite place, and then you can study it just as though it was like anywhere else. So conformal is useful when you're thinking about things which have no mass. You see, photons have no mass, so they're a good thing to think about conformally. Mass adds another ingredient. And it's a little bit difficult to get round to Twistor here, you see, because the idea was to think of conformal invariance.
Because as I understand correctly, in the Twistor story, space-time points stop to play the main role, the basic role, for occurrence of physical phenomena. Space-time points are secondary construction,
yes,
and the primary is Twistor.
Yes, well, think of them as light rays, but the Twistor is more complicated because that's where you consider the spin of the photon. See, when it has spin, it's not localized, and it becomes spread out to some degree. And the way you can describe this in terms of this twisting configuration, and I had a nice way of describing this, and the advantage of this, I should go back to the other story, was to describe positive and negative frequencies in a conformally invariant way, because the normal way people do it, it's not conformally invariant. It depends on the metric. But for electromagnetism, I wanted to have it conformal invariant. So how do you describe that in a nice geometrical way? And this was the origin of twistor theory, because the original thought, it's quite hard to explain these things without being a little bit technical. But let me just explain. There is a structure called a Riemann sphere. You see, you have to think first of all of complex numbers. Now, a complex number involves the square root of -1. You see, in ordinary mathematics, you think of real numbers, and the square root of a real number, a positive real number, is another number. But if it's a negative...
here the idea is to use complex number instead of real numbers.
Yes, the complex numbers are absolutely fundamental. You see, they're fundamental to quantum mechanics. The whole structure of quantum mechanics depends on complex numbers. The wave function of a photon, the wave function of any system, is a complex number system. So when you think of the Schrödinger equation, which talks about the evolution of a wave function, this really is a complex equation. So in order to understand the physics of quantum mechanics, you need to understand about complex numbers. Now, complex number is called complex because it's not simple. As I say, it involves not only a real number, but an imaginary, what people call an imaginary number. We don't like to think of it as imaginary in mathematics because it's just as real as a real number in a certain sense. But you can't see it so directly. You see the way that a ruler measures in one direction, and it measures in terms of real numbers. But a complex number involves a real number and an imaginary number together. And it forms a very beautiful algebra and calculus, which sort of extends from the ordinary algebra and calculus of real numbers to the complex numbers, which are essential for quantum mechanics. Now, you can understand this problem of the positive and negative frequencies very nicely in terms of complex numbers. See, basically it says, you have to think of the complex plane. The complex plane, or the Wessel plane, I guess it was Wessel who first thought of it. People call it the Gauss plane sometimes. Gauss was probably a little bit later than Wessel. Usually he was before everybody else, but in this case I think he was a bit later. Then you sort of have a picture where you have the real numbers going off along one axis, and then the imaginary numbers involving the square roots of negative numbers. I is the square root of -1, and then the multiples of I go up in one day, and the multiples of -I go that way. And you have a plane. So all the complex numbers are represented on this plane. A point on that plane represents a complex number.
Twistors arise from mathematics of complex number.
Yes, very much so. It's absolutely crucial to the subject. And the idea was to make the fundamental principle of quantum field theory, which is to split your fields into positive and negative frequencies. So you do this in a nice geometrical way, rather than talking about the Fourier decomposition, which is a bit complicated. And it does it in a conformally invariant way. So you could talk about the physics being conformally invariant, which I should say really applies to things without mass. When they have mass, then it's more complicated. But originally, twistor theory is concerned with things without mass. So then you can talk about the positive and negative frequency very nicely, because, you see, what I was trying to do, it's hard to explain these ideas because they're very mathematical. You see, you have to think of how you describe this notion of positive and negative frequency. In one dimension, it's quite easy because you think of the complex plane, and the functions which extend into one half are positive frequency, and the ones which extend into the other half, when I say one half, I mean you have the real axis, and then you've got one half of the complex plane goes up, the other part goes down, and those functions which go up are the positive frequency ones, and the ones which go down are the negative frequency ones. So you have a very nice picture of positive and negative frequency splitting in this geometrical way. Now, how do you do that for the full four-dimensional space-time? See, that's just one dimension. If you're talking about one time dimension, that's fine. That's a good picture. But if you want to talk all together for space-time, how do you do this for space-time? Well, you can make space-time complex, but that doesn't help too much, because in this complex, you have an eight-dimensional space. You see, each space dimension becomes 2. Each time dimension becomes 2 again. So 3 space dimensions become 6. The 2 time dimensions become 2 more, and that gives you an 8-dimensional space. And how do you see in this 8-dimensional space how to split functions into their positive and negative frequency? It doesn't work anymore because your real space doesn't divide it in 2 halves, because it's only 4 dimensions sitting inside an 8-dimensional space. That doesn't cut it in 2 halves. It's just a little 4 dimensions is a tiny little sliver in this huge 8-dimensional space. So to try and do this splitting in a nice geometrical way, the idea I had was to say, you don't think of points, you think of the light rays. And the light rays in space-time form a 5-dimensional space. Now, the twistors involve the light rays which spin round, so that you think of the photon having angular momentum as well, or spin. You see it has a spin. Yeah. Then they incorporate the other dimension, and so you get 6 dimensions. So you have the space, which is the twistor space, which is 6-dimensional, and this does split in 2 halves, because the real light ray space is 5-dimensional, and the space of the twistors, these are what I call projective twistors actually, but never mind about that. This twistor space is 6-dimensional. So 5 does split it into 2 halves. And so the ones which go one way are the positive frequency, and the ones that go the other way are the negative frequency. And so this gives you a very nice geometrical way of thinking of this key property needed for quantum field theory. And that was the original motivation of twistor theory. Now the subject has got developed in much, much more complicated ways, and you can describe fields, you can describe Maxwell's equations very nicely in the subject, and you can see where the positive and negative frequencies work and make it quantum mechanical, and all these things become nice. It becomes a nice geometry. It was nice for me because I think visually, and I like to think of things in geometrical way.
Because you are geometry.
Yes, I think very geometrically.
On the website of the Columbia University,
yes,
there is this sentence about you and twistor theory. His work on twistors is the most important new idea about the space-time geometry post-Einstein, and we believe it will be studied long after string theory.
Well, I hope that's true. You see, string theory, the main trouble with string theory, in my view, is that it's not very carefully focused on the dimensionality of space-time. Originally, the idea of strings quite appealed to me when I heard about it. But then when they said, it only works in 26 dimensions. So, okay, well, that's the end as far as I'm concerned. That's the wrong number of dimensions. Then they got it down to 10 dimensions, which seemed to be an improvement, but it's a long way along from the 4 dimensions we need for space-time. So I didn't get very excited about twistor theory. When I learnt it, you had to do it in 10 dimensions or 26 dimensions, or 10 and 26 at the same time, which was even more confusing to me. It didn't really make geometrical sense. Now, there have ways of dealing with this in string theory, but it's not very natural, and it doesn't really fit in with the geometry of space-time in a nice way. So I never, after the dimensionality became too big, I gave up on the subject, although I was quite attractive to the original ideas of it, but not after it became 10 and 26 dimensions at the same time, and now 11. It all seems to me not focused directly on the space we live in. The space we live in has 4 space and 1 time, 3 space and 1 time dimension. and it's four-dimensional with that particular signature. See, 1 and 3. That's important too, because the twistor theory relates very specifically to space-time with 1 time and 3 space. And the way it works, I should say there are variants of twistor theory, because after developing some of these ideas, the mathematicians picked up, actually interestingly, because they supplied some useful ideas in the twistor, particularly Michael Atiyah, who was a friend of mine, and we were in the same institute in Oxford for a while, and I learnt a lot of the mathematics that is needed for twistor theory. Some of these ideas which involve a quality known as cohomology. And cohomology is very necessary as part of twistor theory if you want to describe fields like electromagnetism. If you want to describe the Maxwell field in twistor theory, you have to bring in this mathematical notion of cohomology, which fits in very beautifully with twistor theory. And so I needed this input from the mathematicians, particularly Michael Atiyah. And then the mathematicians picked up on some of these ideas in twistor theory, how you describe nonlinear fields and things like this. And this became a sizable subject within mathematics. And so it's developed in certain directions which are not exactly the same. I should say there are certain differences. I'm not quite sure how to say this. You see, it depends on the geometry of space-time. It has what's called a Minkowskian signature. Mm-hmm. So you have 1 time and 3 space. So it's not just like a 4-dimensional space-time. It's very specific to 1 time and 3 space. And the twistors work very naturally in that framework. Now, if you're just doing pure mathematics, as the mathematicians are, then they like to have it 4 space dimensions, all 4, you see. They don't like 1 and 3. They like them to be...
I can give you an example. Maybe that's the answer for that question.
Yes.
Professor Maciej Dunajski, a Polish scientist from University of Cambridge,
yes,
who works on the theory of twistors, yes, wrote to me a few days ago this email. In the last few months, I have been most scientifically involved in the so-called twistor theory, in which a breakthrough has occurred. We had a program on this topic in Cambridge in September, and Roger Penrose came in person. It seems that the almost 60 years old idea of unifying the theory of gravity and quantum theory may have a positive solution in this theory.
Yes. Well, I've worked with Maciej Dunajski for quite a long time, and he's a very skillful mathematician who understands about twistor theory very much. I think the thing specific, you see, twistor theory is very specific to space-time geometry. It's, you see, if you take the formalism of general relativity, it depends on Riemannian, or what you call pseudo-Riemannian geometry. The pseudo means that you've got only 1 time and 3 space, so it's not really Riemannian geometry. Riemannian geometry is when you have four space dimensions, mm-hmm, but it's curved. And Einstein needed this theory to develop general relativity. It was absolutely, he couldn't have done it otherwise. And he had to have a mathematician to help him to learn the needed geometry, differential geometry, Riemannian geometry, which is the geometry of curved spaces of any dimension. And it's very specific, it's not any dimension, because the general relativity theory requires 4 dimensions. And it's not ordinary Riemannian geometry, because it has 1 time and 3 space. So it's what people call pseudo-Riemannian geometry. Now, twistor theory is very geared. When I say twistor theory, I mean what I mean by the kind of twistor theory that I work on, and which is geared to looking at physics. the mathematicians have picked up on twistor theory very much, and they have a different version of twistor theory, where instead of having 1 time and 3 space, it's though you have 4 space dimensions. And that's a different kind of twistor theory. It's what I'm calling pseudo-twistor theory, if you like, because if you like, the kind of geometry which is useful for general relativity is pseudo-Riemannian geometry. It's not, the signature is different. The number of pluses and minuses you have. See, in ordinary distance, Riemannian distance or Euclidean distance, if you have a triangle, well, if you want, in ordinary coordinates, you want the distance between 2 points. It's the sum of squares. You take the square root of the sum of squares. But in Minkowski geometry, this was the idea that was introduced by Minkowski in order to understand special relativity. When Einstein first heard about it, he didn't like it at all. It was quite ironic. But later on, it was crucial to his development of general relativity. Because, you see, Minkowski geometry has 1 time and 3 space. It's very specific to that kind of geometry. And that's what special relativity depends upon. And when Einstein got finally converted to Minkowski's ideas, he realized that that's what you need to make that kind of geometry curved, and then you talk about gravity. So that the gravity is incorporated into the theory once your Minkowski space is not so much Minkowski anymore, but it's curved in this way, which describes the gravity.
This is right, that the twistors theory can unify the gravity theory and quantum theory.
Well, you see, it may be, I'm not sure what Maciek was saying in the comment he was making there, but you see, there is a development of twistor theory, which I call bitwistors. There's a certain irony about all this. Let me explain the irony. When I was originally starting on this,
60 years ago.
This was in 1962.
Almost 60 years, more than 60 years ago.
Yes, more than 10 years.
More.
1962. When I was thinking about the positive and negative frequency problem. And that was the initial motivation. But then a little later, when I started to work out Maxwell equations and the fields and all that, it became, we were talking about positive and negative frequency. Sorry, positive and negative helicity. So that's your photon spins right-handed or left-handed, see? And that are the 2 kinds of spin you have. And the 2 halves of twistor space became more connected with helicity, right-handed or left-handed, than frequency, which is positive or negative. And this led to what I call the fundamental confusion of twistor theory. Because when I started to develop curved twistor theory to try and fit in with general relativity, I produced a thing which I call the nonlinear graviton. This was the first time that curved twistor theory came in. And it did make a curved twistor space. And when you make the curved twistor space, you can incorporate the spin of a graviton. So a graviton would be the gravitational particle, like the photon describes the particle for electromagnetic field. When you quantize it, the light becomes particular, if you like, particle-like. As we know, photons have this particle characteristic and they have the wave characteristic, and quantum theory is needed to bring these things together. And the idea is that general relativity, which talks about gravity, should have the same sort of character. You have the particle form of gravity, which would be gravitons, and the wave form, which would be gravitational fields, as we understand them. Well, nobody has observed a graviton, because the energies would be all difficult to observe directly. So that's part of what one might call quantizing gravity. So the quantum theory of gravity would involve making the gravitational field consistent with a kind of graviton picture of gravity. Now this particular solution I found well, it wasn't a particular solution, it's a class of solutions which describe gravitons in accordance with general relativity. So they are curved, they're not flat. They're actually curved spaces, but they involve this fundamental confusion of twistor theory because the helicity and the spin, the helicity and the frequency become mixed together. So to describe that, the graviton should have positive frequency. A proper graviton should have positive frequency. But when you try to do it with twistor theory, it has positive helicity at the same time. So these two ideas get joined up together, and they only sort of half describe the quantized gravitational structure. So they only half describe when I say only half describe, they only describe half of the gravitons. Those are the ones which spin, I think it's left-handed, yes. Not right. It depends on your conventions, you see. And this was a very puzzling situation. It came about because of this confusion, which is inherent in twistor theory as it started. The confusion was the positive frequency and the positive helicity. And they are both together in twistor theory. Now you can separate them if you take what you call dual twistors. You can take the twistor space or the dual twistor space. Now the dual twistor space is very similar to twistor space, but it's the other way around. So instead of the positive frequency being the positive helicity, I forget whether it's positive or negative now, negative helicity, it's the other way around for the dual ones. So the idea I had and described in the Cambridge conference is how you fit these two ideas together. And you make a structure which I refer to as bitwistors. You have to have them, instead of being a four complex dimensional space, as twistor theory is, ordinary twistor theory involves four complex dimensions, but you might want to make it three complex dimensions when you talk about projective space, rather than the vector space. The projective space, that's a mathematical concept which is like projective geometry, you see. But the projective geometry, when it's complex projective geometry, this is the six-dimensional space where each real dimension becomes complex.
The twistor theory versus other Penrose theories.
From all your theories, from human consciousness, you try to answer the question how human consciousness was born, through the questions about black hole, twistor story is the most important for you?
It's the most developed, yes. You see, the consciousness thing is an idea.
I thought that the most developed are that connected with black hole.
No, twistor theory is much more developed as a subject.
Mm-hmm.
I mean, the black holes are more direct because we have evidence for them. They're there. And I guess that's what the Nobel Prize was for.
Yeah.
So the black holes...
Because we have pictures.
Yes,
pictures.
And they are an important part of physics, quite clearly. But they sort of fit in with twistor. You see, the missing thing in twistor theory had been, and I think it needs more development, the missing theory is how you combine twistor theory with general relativity, with proper curved space-times. And you could do it partially by confusing the spin with the helicity. And so these describe left-handed gravitons. Now you want to have both left-handed and right-handed to make a proper theory of the quantum gravitational field, if you like. So you need both-handedness. And the idea which I developed only rather recently, over the last few years, and I wrote a paper in honor of C.N. Yang, who was becoming 100 years old. He is 100 he's 102 or something like that now, I think. And he was very famous for developing the theory of weak interactions with Lee, so Yang and Lee. And it's the important part of that theory is it's handed. You see, left-handed and right-handed are not the same. And weak interactions, apparently unique amongst physical theories, are not left-right symmetrical. See, most of physics is left-right symmetrical. If you have the theory it describes left-handed, it's right-handed, it describes left-handed at the same time. So this applies to almost all physics. However, the weak interactions, that's not true. And they have a handedness. And Yang and Lee got the Nobel Prize for developing this theory of weak interactions, which involves a handedness. Now, the article I wrote for Yang's 100th birthday was developing, if you like, the theory is going the other way. You see, it's quite ironic in a way because it's making Twistor theory not handed. You see, Twistor theory was very much a sort of left-handed theory, if you like. And the graviton comes out as being necessarily left-handed. But you don't want that to describe gravity because it's not a left-handed theory. It's a theory which involves both left and right. So what you do in my later what I was describing in Cambridge was this idea how you take the normal Twistor theory, which, if you like, is left-handed, and you take dual Twistor theory, which is right-handed. But that's just changing a sign. It's not doing anything clever. You can have these two theories. But what you do is you bring them together. And the important thing when you bring them together is that it brings quantum mechanics in. You see, if you stick with one side or the other, then the Twistor theory is not quantum mechanical. It's classical, really. But when you put the two sides together, it's like, how would I put it? It's like position and momentum. See, in quantum mechanics, position and momentum are what are called canonical conjugates. So position, if you have a state of a particle which is well defined in its position, then it's completely undefined in its momentum. And the other way around. If it's well defined in its momentum, then it's completely undefined in its position. And most things are sort of in between. So they're fairly well defined position and fairly well defined momentum. But these notions are called conjugate, the canonical conjugates. And you have in quantum theory, this is the Heisenberg idea, which really started off quantum mechanics. You have these things which do not commute. AB is not equal to BA. So if you have if you work just with position, then AB is equal to BA. If you work just with momentum, then AB is equal to BA. But if you want to have position and momentum together, then AB minus BA is the other one. So you have to bring them together. So that the way the mathematics works is that what's called the commutator, that's to say, why isn't AB equal to BA? Well, you look at the difference between AB and BA, and it involves the other thing. So if you do this for position, then you get momentum. And you do it for momentum, you get position. And this is the sort of fundamental thing in quantum mechanics. Now that idea comes into Twistor theory. And it comes in that the twistors, what's the canonical conjugate of twistors? It's the dual twistors. So you have the twistors and the dual twistors, and one of them is the canonical conjugate of the other, and the other is the canonical conjugate of the one. So that when you do it with quantum theory, and AB is not equal to BA, but AB minus BA involves the other thing, and the AB minus BA, the other thing, involves the one thing. These are the conjugate variables. Now in crystal theory, the conjugate variables are twistors and the dual twistors. So those are conjugate to each other. Now you make an algebra which involves both twistors and the dual twistors. And when you make that algebra, it has quite curious implications which might seem to involve things like particle physics. I think that hasn't been developed, I should say. That's only an idea. But I think there's a reasonable chance that the ideas that, well, when it talks about strong interactions, that's the interactions which hold particles together.
How can the twistor theory help us?
Which are the most fundamental questions we can find when we ever confirm Twistor's theory in all details?
Which it's as a mathematical theory, it doesn't need confirmation. It's just a theory. It's just a mathematical structure. This I'm talking now about things which haven't been developed. So I'm speculating now.
Yep.
This is speculation. Okay. Now I think it's quite possible that these bi-twistors, which do involve both the twistors and the dual twistors, so you are enabled to talk about left-handed and right-handed together. And I think they would enable you to talk about general relativity together. This is still not achieved yet, but I think there are good indications that this could be done. Now, could it go beyond that and talk about how the quantum aspects of general relativity are brought out? This is speculation. I don't know. Does it fit in with particle physics? Up to this point, it doesn't. I remember I had an idea about how to make particle physics fit in with twistor theory. And I remember I was visiting Caltech at one point, and I think Stephen Hawking was there, and he arranged a meeting between me and Richard Feynman. And I talked about twistors to Richard Feynman. And I asked him about some ideas I had about particle physics. And he was very good. He said, don't follow that. That's not going to be useful. But do follow what you're doing on twistor theory. He thought that was a good idea. So I give him credit, because the particular idea I was looking at for particle physics was probably completely wrong. And he was noticing that it was not a fruitful idea. So far, particle physics has not really fitted in with twistor theory. Now, I think there is a reasonable chance that it would fit in with bi-twistor theory. The reason I'm saying this initially, this is speculation. I don't know to what extent this is correct. But the theory of strong interactions, you see, in particle physics you have weak interactions, that's the Yang and Lee business, which I mentioned before, which have a handedness to them.
Yes.
And there are gravitational interactions, which don't really form part of normal particle physics. And you've got these strong interactions. Now, the strong interactions are strong because they dwarf everything else.
Strong. Yep.
And they hold the particles together, if you like. They're the main thing which dominates the particle physics. Now, how do they fit in with twistor theory? Well, they might do, because of when you do the bi-twistors and you look at the way that the twistors and bi-twistors fit together, you find there is a very nice kind of triple product. How to explain this? It's a bit like, see, when you go back to Hamilton, Hamilton was a very distinguished mathematical physicist, and many of the ideas become important in physics, Hamiltonians and things like this. But what excited him the most was his discovery of quaternions. This was a kind of algebra which you see, rather than the complex numbers, which describe one space of time, it's only a two-dimensional space. The quaternions talk about a three-dimensional space. But the key thing about it is that AB is not equal to BA. And he formed this algebra, which is called quaternions. And this quaternionic algebra, Hamilton got very sold on it, and he spent the rest of his life, many people say he wasted the rest of his life on developing a theory of quaternions. Now, it's a bit mixed story, this, you see. But very shortly after Hamilton discovered his quaternions, other people, I think there were about 3 mathematicians independently, saw how to develop this idea into what are called octonions. And these are not just four-dimensional structures, they're eight-dimensional. And they, you see, Hamilton's quaternions have AB is not equal to BA. The octonians have a more complicated thing, that A times B times C is not the same as A times B times C. So it depends where you put the bracket. AB times C is not the same as A times BC. So it's a little more complicated piece of...
But today we know that it's not true.
You see, it's not true in the octonian algebra. You see, the quaternions, it is true.
Mm-hmm.
So the octonians, it's not true. Now, I had a phase of thinking, I wonder whether octonians in the split form, you see there, again, it's the signature question. Do you have 3 pluses and 1 minus in space-time? Now, there is another version of octonians, which is called split octonians. And those, instead of having all pluses, normal octonians have 8 pluses, or, well, there's 7 pluses because it's 8 things which are added together. And that's the structure which it's developed on. But there's a special kind of octonians called split octonians, where you have 4 pluses and 4 minuses. And I often wondered whether this had anything to do with twistor theory. And what I finally realized is it does have something to do with the bitwistor theory. That the bitwistor theory, you can construct the octonians, or the split octonians. So it really is connected with the split octonians. And the question is, do these split octonians have anything to do with particle physics? I think they may well do, mainly because in this construction of the split octonians, you have a, you see, yes, you have a triple, you see, how to say this? See, the quaternions involved a thing which is called a vector product.
Mm-hmm.
You have the scalar part and the vector part. And when you multiply the vectors together, you do this with this construction of what's called the cross product. So you have 2 vectors and you produce another vector at right angles to the 2. So you have 2 in space, in ordinary 3 space. 2, 1 there, that there, and then the product points perpendicular to the plane of the 2. But AB is not the same as BA. So you have this Hamiltonian structure for the quaternions, that AB is not BA. But ABC is still the same as ABC. You see what I mean? But the octonians go one step beyond that, and you have an 8-dimensional structure where this algebra for ABC, or AB times C, is not the same as A times BC.
When I'm hearing you now, I think that the abstractional thinking is the never-ending story.
Well, it's I hope never-ending. You see, it does end in a certain sense, because there are certain theorems. If you have the associative rule, which is ABC, well, then you stick at 4 dimensions. And if you have the octonian rule with the what they call the alternative rule, which is another algebraic structure. But AB times C is not the same as A times BC. You have these octonians, but you stuck there. That's the end. You see, you might say it's an unending story. In a certain sense, it is, because you can talk about groups and they get bigger and bigger and it gets huge, you see. But if you want about these algebras, they do stop. And they stop at the octonians. And this may well be, you see, particle physics really stops at a certain point. It doesn't keep on going. The space-time structure only stops at a certain point. You've only got 3 space and 1 time. So it's not as though physics is more, I mean, it doesn't, how do I put this? See, mathematically, you can go endlessly complicated. But physics is only interested in certain aspects of mathematics.
Yeah. If something exists in the nature.
Yes, that's right.
Thank you very much for your time.
Right. Okay, my pleasure. Yeah, it's been good fun. Thank you.
Subscribe our channel to watch next interviews with Sir Roger Penrose.